Good afternoon to everyone. I'm Dr. S. Vivekanandan, heading Department of Instrumentation in VIT, Velo. It gives me immense pleasure to be a resource person for this 5-day ATAL-sponsored online faculty development program on instrumentation and telemedicine, organized by the Department of Instrumentation Control Engineering, Sri Krishna College of Engineering and Technology, Coimbatore. Thanks to the management of Sri Krishna College of Engineering and Technology, department head, faculty members, and staff members of the department. And special thanks to Dr. Chinadurai and Dr. Narendran and the other coordinators for conducting this kind of events. It always makes me happy and excited to see or be a part of a group where instrumentation fraternity are there. Thanks to all the participants of this event. Next slide, please.
Yes.
My presentation will have a general introduction and about smart sensors, about IoT, and a case study of a smart sensor with IoT in diabetes, and various research grants related to biomedical instrumentation field. Can I have the next slide? Thank you. Till human exists, I'm sure that there will be a demand in biomedical instrument and its related research. So biomedical engineering is a rapidly evolving a cross-disciplinary field that involves medicine, biology, chemistry, engineering, nanotechnology, and computer science. We can say this as a multidisciplinary, like a decade before, but now it is transdisciplinary. Okay, you have to call this as a transdisciplinary field. So bioengineers are at the forefront of scientific discovery, creating innovative medical devices, vaccines, disease management, the products, robots, and algorithms that improve human health around the world. So the challenges which we are facing in a public health or in medicine or in general the biomedical instrumentation are most of the diseases now shifted from an acute to a chronic level kind of conditions, and aging is a big aging of our population is a big issue, and the issue and diseases related to aging is a challenging to our public health department. And we have global health disparities. There is a difference because we have each and every area changes. So there is a difference, there is a disparity in health from one country to another country. So that is also a challenge. That's also a challenge in public health. And we have an emerging and re-emerging infectious devices. And we can call this as a pandemic disease also, not just an infectious diseases. Now it becomes a pandemic device. So it is emerging, and we can say after 10 or 20 years, it's going to re-emerge. So each and every diseases is going to re-emerge. Long back, we said we said we have eradicated chickenpox, but now it is coming. Long back, we said we have eradicated leprosy, but now it is slowly starting this kind of diseases in our human health. So these are the challenges. Apart from that, we have non-communicable diseases like depression, allergy, obesity. Now India and Tamil Nadu, we can say that we are number one in this kind of non-communicable disease. So this is what about a small introduction about the biomedical engineering and the challenges in health and medicine. Can I have the next slide, please?
Sir.
So based on this, there is a need to align with the transformation of medicine and health in the 21st century. There is a difference we have between 20th century with that of the 21st century. Initially, like in 20th century, we used to treat disease when symptoms appear and normal function is lost. After everything is normal function is lost, and when system appears, we used to treat the disease. Whereas now we intervene before symptoms appears and preserve normal functions as long as possible. And
so your audio has got cut.
Hello.
Vivekanandan sir, I think your audio is not clear. It's not coming.
Is it coming now? Hello?
Yes, sir.
Yes, it is coming. It is coming.
Hello?
Yes, sir. You're audible, sir.
Is it fine now?
Now
Is it fine
yes,
now?
sir, audible, sir. Yes, sir. Yes, sir. Yes, sir.
Now it's fine, sir.
Yeah, can I? Yeah, thank you, thank you.
Yes, sir. Yes, sir.
Can I go to the presentation?
Yes, sir.
Thank you. So in 20th century, we did not understand the molecular and cellular events that lead to diseases, whereas now we understand the entire molecular structures and we have the ability to detect the patients at risk. Even this pandemic, the COVID-19, we are in the position to understand the molecular structure and the characteristics and the behavior of each of the viruses, and we are in the position to come with some vaccinations too. So that's the difference we have with the 20th century with that of the with 21st century. And we used to fragment, we used to expensive, it is used to be an expensive in financial and disability cost, whereas now we focus on unmet needs and provide a total integrated solutions. It's not just for only one, we used to give it for a integrated solutions. So this is the difference we have from 20th century to 21st century. So based on the need, we have to align ourselves with the public, with the challenges we have in our public health and medicine. Can I go to the next slide, please? Yeah. Next slide. Yeah. Before discussing to the topic, I want to deliberately discuss on the 4 basic principles to improve one's health. That we call it as 4P. One is predictive, second is personalized, third is preventive, fourth is participatory. Predictive, or the first in the sense personalized. We know that people are diverse. So is there so is their personal health too. We have different DNAs, we have different immune system living in different parts of the world. So the objective of personalized is to adopt healthcare to your personal health system and what is best for you. So it means that personalized for each and everything, it varies. So we have to personalize the medicine, the research, and everything has to be personalized. If it is personalized, then we can improve our health and we can even improve our research too. So that's the point of personalizing it. Second thing is prediction or predictive. It means that, see, we know we have machine learning, we have artificial intelligence, we have various technologies. So these technologies give us new way to predict health events and enable the foundation of prevention. So the last one is the prevention that we are going to do it. So we used to predict the diseases, we used to predict the issue, and we used to do it. So that kind of activity has to be done. That is what prediction deals to. The third one is nothing but preventive, which means that not only taking actions to prevent a particular diseases or its symptom, but also contributing to live a healthy lifestyle and prevent a whole range of risk factors which might impair your health. So so the entire preventive measures has to be taken. And the last one is nothing but participatory. To be at the center, one's healthcare treatment sound obvious, but it is not often. So clinicians are often under time pressure and treatments are complex. So the patients need to access the information. They have to do self-care, and they should be in the position, or they should be able to take their ownership of their health. Uh, of their health. So these are the 4 P's we have to think of for improving our health. It is not just these 4 P's can be used for health alone, to improve our health alone. It can also be used for our biomedical research too. One has to be predictive, personalized, participate, and preventive. So if we have these 4 P's, with these 4 P's, I'm sure that we'll have a very good output, very good research output. Can I have the next slide, please?
Yes.
Yeah. So these are the below 10 or the hottest bioengineering R&D trends happening in 2020. Most of them are, the first one is tissue engineering. Second one is transdermal patches. Third one, wearable devices. Fourth one, robotic surgeons and rehabilitations. Next is nano robots. The next is virtual reality. Next is microbubbles, prime editing, organs on chip, and mini bioreactors. Or these are the various hottest bioengineering and biomedical related research and development going all around the world. The first one, I'm just going to in depth before smart sensors and before IoT. I just wanted to give you a small introduction about the recent trends going in bioengineering research and development. Next slide, please. The first is nothing but the tissue engineering. So tissue engineering is simple. Living tissue can be made from the biological active cells, which are deposited on a scaffolds in controlled condition. A popular deposition method is bioprinting, which is nothing but a process of very similar like 3D kind of printing is used. Instead of inks, we used to go with bio inks, which consists of human cells instead of a plastic thing. So that kind of bioprints has to be made. So that the cells are printed in the thin layer that accumulate in the living tissue or body parts that can be implanted. So there is a research at Wake Forest Institute for Regenerative Medicine. They are doing a special kind of 3D printer to create a tissue that thrive when implanted in rodents. So this is the first kind of bioprinting is happening, and which was done in Wake Forest Institute for Regenerative Medicine. So the second thing which I wanted to discuss is transdermal patches, which are nothing but which have come a long way since their used as a method to break nicotine addiction. It's not just for the nicotine addiction alone. This can be used for greater variety of applications. For example, as a given, NTU in Singapore has created a transdermal patches filled with drug that help fight for obesity. So instead of taking it orally or through injections, these compounds has to be released in our body as a biodegradable micro needles, and that will slowly be released into our body structure. So which makes us or controls our obesity. It is not just for obesity; it can be used for various purposes. But the first thing was used only for nicotine addictions. Can you go for the next slide, please? Yeah, the next thing is nothing but the wearable devices. So wearable devices, everyone know it, and everyone are wearing a watch kind of devices. That is what common all around the world. But apart from that kind of wearable devices, which can give you heart, blood pressure, pulse rate, and that has to be transmitted in real time medical facility. Apart from this, we have a technique called smart clothing. Smart clothing. So this smart clothing controls the entire body temperature by using a special polymer and humidity responsive vents that open when needed. So based on the need, it opens so that we'll have a based on the temperature of our internal body, our clothing can be changed. So that kind of smart clothing is now under research. So it has been proposed that individualized temperature control through clothing could reduce even a building's heating and cooling costs up to 15%. So apart from the wearable devices which we use to do it, this is another kind of research in clothing, and this can also be used for our building structures too. So that kind of activity is going around our world. The next thing is robotic surgeons. So we used to see lots of robots in various applications, but now it is used for the field of rehabilitations. The robot manufacturers are making multifunctional robots to assist surgeons in their operating room. So, for example, the Locomat is a gait training system that utilizes a robotic exoskeleton and a treadmill to help patients regain basic walking function. So for rehabilitation just because of the backbone damage, or even because of our brain damage. So we'll have a long rehabilitation period where their muscles and nerves are disabled. So the muscles has to be regenerated. For that, with the help of robotic surgeons and with the help of robots, we are regaining their regaining their functionals. So that's a good research happening all over the world. Next slide, please. Apart from this robotic surgeons, we have nano robots too. So the nano robots design includes our DNA based structures, which can be used for killing the cancer tumors. So that the robot can be released into as a drug into our body, which can usually we used to use it for digital image processing kind of technique. Whereas now that can be used as a drug to kill the cancer tumors. So that is what the research now is going on. By delivering the pharmaceutical agents exactly where they are needed, the body is not overloaded with the toxicity, and the side effects are fewer or less intense. We cannot say there is no side effect. It is of less intense, improving the patient's experience. So that kind of tumor precisely can be it can kill the cancer tumor. So this is the fifth kind of field I just wanted to deliver. Apart from that, we have virtual reality. I think most of us know about VR. VR is an especially valuable tool in a medical field because of how it can present the detailed data taken for a 3D medical images. So VR is a very valuable tool. It's also critical teaching tool. It can be used for medical students. For example, as it is given, it can be it could perform virtual dissections instead of using cadavers. I think there are advertisements too. The biomedical for physicians, virtual reality is used for educating the various organs. Various organs we can take from the laptop, and we can show the 3D view of all the organs, internal organs, and the internal organs of our human body. So this virtual reality, apart from using as a I think as a tool for medical field, can also be used for educating our students. Can you go for the next slide, please? The next one is called Microbubbles. So this is nothing but which can deliver drugs to specific targets, thereby avoiding damage to the health cells and tissues. I think most of us might be knowing that killing the cancer cell is a big deal. Instead of killing that tumor alone, the physicians used to kill the entire healthy cells and tissues too. So there is a research going called microbubbles, which can be used only for that specific targets. That area alone can be killed instead of killing the health tissue and cells. So I think Mr. Beta Chertok is an assistant professor of pharmaceutical sciences and biomedical engineering at Michigan. He was telling that microbubbles loaded with drugs can be injected into the body, and they will distribute everywhere. But I can then disturb that microbubbles by an ultrasound beam, and the drug will be delivered, especially where the drug is needed. So that kind of activity is under research. So apart from this, we have a research area called prime editing. So this new gene editing technique builds on success of base editing with CRISPR. That's a technology. So prime editing rewrites our DNA itself by only cutting a single stranded, add or remove or replace our base pairs. So that can also be done. So this is research is going on in a healthcare and Broad Institute of Hardware Technology and MIT. It is under research. So the replacement or addition or removal kind of DNA itself is under research. So this combination, all our 10 various different fields I'm discussing are related with bioengineering and biomedical instrumentation. So can I go to the next slide, please? Can I go to the next slide, please? Yeah. So the next thing is called organ on a chip. So it's known to us that there is a chip technology which allow the construction of micro-scale models that simulate human physiology outside of the body. So that has to be implemented in our body. So organ on chips are usually used to study the behavior of tissue and organs in tiny but fully functional sample sizes to better understand tissue behavior, the disease progression, and the pharmaceutical interactions. So that can be easily done. So for example, inflammation process can be studied to determine how inflammation is triggered and its value as an early warming indicator for underlying medical conditions. So organ on a chip can be implemented in our body so that we can have a study. Apart from study, that can also be used for troubleshooting all the other issues too. The last one is nothing but mini bioreactors. So we know that bioreactors are systems that support biological active organisms, and their byproducts, the smaller bioreactor, are easier to manage and require less sample volumes. Advances in microfluidic fabrication capability now make it possible to design micro-scale bioreactors. So based on this fabrication technology, we can have micro-scale bioreactors that can incorporate enzymes or other biocatalysts, as well as the precision extraction system to produce highly pure products. This can also be used as a 3D printing becomes more refined. It should be possible to manufacture miniature bioreactors with more unusual flow paths or specially designed culture chambers. So these are the 10 different research going on around the world. Can I go for the next slide? My today's discussion is about smart sensor and IoT and an application of smart sensor with IoT based on diabetes. So we all know that a sensor is nothing but a device that responds to a physical stimulus, either it may be a heat, light, temperature, or whatever it is. And the device which performs an output function are generally called as an actuator. The one which does all this system, the output functions is nothing but the actuator that are used to be controlled some external devices. Either it may be a movement or whatever may be the thing that can be actuated with the help yeah. So this both sensors and the combination of sensors and actuators are known as transducer, and we all know that it is used to convert one form of energy into another form. Whereas coming to the point of smart sensor, see, very simple that I can tell you any engineer will become a smart engineer if he knows a sensors and networking technology. Any field, say for example, a normal energy meter can be converted into a smart energy meter if a sensor and a networking is incorporated. It's like smart city, smart parking system, whatever be the smart things, whatever be the application, when a sensor or networking sensor and a networking technology is connected to that device, it becomes a smart application. So that a smart sensor is nothing but an analog or a digital transducer combined with a processing unit and a communication interface. That's what a processing unit and a communication interface. It consists of a transduction element, a signal conditioning, a controller, and an intelligent, some intelligence in a single package. So this integrated sensor, which has an electronics and the transduction element together on one single chip, is nothing but a system on chip. We used to call as SoC. The main aim of integrating the entire electronics and the sensors is to make a system and an intelligent system or an intelligent sensor, which can be called as a smart sensor. So which can decide, which can think on its own and come to a conclusion. Can you go for the next slide, please? In general, the various architecture of a smart sensor, as I said before, it should have a sensing and transduction element. It should have an amplifier. It should have a sample and hold, an analog multiplexer, an ADC, a DAC, and you should have a memory and communication with a processor. Coming to the next thing, well, this shows the block diagram of a next slide, please. This shows the block diagram of a smart sensor. As I said, I have just taken an RTD, a thermistor with a thermo. Hello. Yeah, it's a combination of what I shown here is nothing but an RTD thermistor with a thermocouple unit, which consists of an RTD which is compensated with the temperature compensation is done with the help of thermocouple. This is small example of smart sensor I have shown here, which consists of an MCU, which consists of integrated circuits. We have a filtering, and we have a power management system. All these things with the timer and the analog and digital conversions. When they are connected, all these are connected with IoT. Either it can be connected with other devices using RS-232 or wireless through antenna. It can be connected to IoT device. This is in general the block diagrammic view of a smart sensor. Can you go for the next slide, please? Next slide, please. Hello.
Sir.
Next slide, please. Next slide, please.
Yes, sir. Yes, sir. Sir, we have a connectivity issue, sir. From our side, we will change it 1 minute, sir. We will change in 1 minute, sir.
Yeah. Yeah. Can I start? Yeah. Can I start? Yeah. So this is the slide which
Yes,
I
sir.
just wanted to tell you that the following are the functions which can be done with smart sensors or any smart sensors are an Sir, I'm getting some disturbance. Sir, I'm getting. Hello. Sir, I'm getting some disturbance from your end. Hello. Yeah. Yes. These are the various functions which can be done by a smart sensor or an intelligent sensor, which are nothing but it can be a data converter, or it can be used for a bidirectional communication. It can take decision on its own, and it performs the logical operations. Can I go for the next slide, please? Yes. So a smart sensor in general, it should have a self-description. It should have a self-identification. It should have it should be self-diagnostics. It should have a self-calibration, testing, and validation, and it should have self-adaptation, and it should have some local awareness, and it should have a self-compensation, and it should also have a multi-sensing and data fusion. So self-description is nothing but it's a description about the sensor itself contained in a sheet or a configuration file. So it should be in the position to describe about itself. Then identification, in the sense it's a information stored in an electronic metadata in the sensor itself. So it should be in the position to be easily identifiable. So that is nothing but self-identification. Self-diagnostics in the sense the process of diagnosing or identifying conditions and error performed by the sensor itself. It should diagnose itself. It should calibrate. It should test itself. At the end, it should also validate. So I think you can understand from the word calibration, testing, and validations. It should be in the position to say that the sensor is perfectly working. It should have a self-calibration technique. It should have a self-testing and validation technique. Apart from that, the main important thing is self-adaptation. So self-adaptation in the sense automatic adaptation to change in the operating environment by a sensor. If there is a change, based on the change in the environment, it should be in the position to change itself. It should adapt itself so that it is not going to be damaged by external or in the operating environment. Then we have a location awareness. It should be in the position to have self-awareness of the physical placement of the sensor and self-compensation. Say, for example, temperature, we have another compensation called with the help of thermocouple. We have an RTD temperature compensation which can be done with the help of thermocouple. So that kind of self-compensation should be there, and it should be in the position to use in a multi-sensing and data fusion. It should sense multiple phenomena using different sensing elements and performs a fusion automatically. It has to be done automatically. So these are the various characteristics of a smart sensors. It should have all these characteristics. Can you go for the next slide? Can I go for the, yeah. Yes. So this is very simple, block diagrammic approach of a general architect of a smart sensors where we can have n number of transducers which has to be amplified, sample and hold, and can be connected in a single analog multiplexer, then can be converted and it can be given to a microprocessor which will be communicated out to output using serial communications. If needed, it should be in the position to have a memory. So this is what an architecture, general architecture of a smart sensor. Next slide, please. And this is nothing but the hybrid. It's not just for a one smart sensor alone. We can have n number of smart sensors which can be connected in a hybrid to a same communications. Say, for example, the first hybrid system, a sensor is connected with ADC and bus interface with the help of universal sensor interfaces. The second configuration shows that shows the connection of a sensor analog system with the digital circuit and bus interface. And the third configuration is nothing but a sensor is combined with an interfacing circuit already to provide duty cycle and bit stream. So this kind of hybrid connection can also be performed. All these connections are on a single chip is said to be standardization. So that should be there in a smart sensor. Can you go for the next slide, please? So this is nothing but the integrated. As I was telling, it should be in the position to have everything on a single chip. Either it may be a magnetic technique, or it may be a chemical, or it may be an optical mechanism, or it may be a mechanical this thing, or it may be a thermal. So everything has to be integrated on a single chip. So this is said to be an integrated smart sensor. So we can integrate all functions from sensors to bus, even to the networking systems can be implemented on a single chip. It is said to be integrated smart sensors, or we can say a single on chip SoC kind of sensors. Sensors is available even nowadays for various applications. Can you go for the next slide? Coming to the fabrication of a sensor, sensor is made with the same technology as integrated circuits. So it's nothing but the same technology which we have in ICs. A smart sensor utilizes the transduction properties of one class of material and electronic properties of silicon. So one problem with silicon is it is not possible to have silicon with proper effects. It is possible to deposit layers of material with the desired sensitivity on the top of silicon substrate. So that is the one problem or disadvantage we can say. You can say in silicon. Apart from that, we have so many other substrates can also be used in our recent research says we can have so many other fabrications. We have even glasses can also be used as a substrate. So solid state integrated sensors are basically composed of 4 elements: a custom fill for transduction. Above that, you have a microstructure. Above that, you have an integrated interface circuitry. Then you have a microcomputer-based signal processing algorithm. So mainly 3 techniques can be used as one: bulk micromachining or surface micromachining and wafer bonding process. These are the processes which are used for fabrication of smart sensor. Next slide, please. This slide shows you the various process in the fabrication of a smart sensor. First, we have to take a wafer, then it has to be oxidized using thermal oxidation, and we can have silicon and an aluminum deposition can be done above that using sputtering and the thermal evaporation technique. And we have to, based on our need, we have to etch it, and it has to be annealed at 550 degree centigrade for 6 hours. This is in general, but apart the example which I have shown here is for a pressure measurement. Using resistance principle. That's the reason. In the next thing, I'm showing it as in aluminum deposition and patterning to form a Wheatstone bridge kind of structure is made here. So this is exclusively for pressure based on resistance changes. Then we have to oxidize the patterning from backside to form a cavity, so that it becomes the backside we can form a cavity kind of structure. Then silicon etching in silicon etching can be done to get a perfect output. So this is what in general the fabrication technology of a smart sensor. What I have shown here is exclusively for pressure measurement using resistive principle. Can you go for the next slide? Yeah, so this slide shows you the standards, the smart sensors standards protocols. If you are using a PMU based smart sensor, we should have a standard of IEEE 1344 or IEEE C 37118-2, or we can even go for IEC standards. Both IEC and IEEE to some extent we are following it. And if it is the network connections, if it is wired, we can have TCP/IP. If it is a wireless, we can have Wi-Fi or LTE, 3G, 4G. Now we can have even 5G LTE cellulars. These are the network connections we have to use for a PMU based smart sensors. If it is an MU based smart sensors, we have to go with the standards called IEC 60044 and IEC 618699 and IEC 618509-2. And the wired, it can be a wired connection or wireless connections. So whatever be the network connections, based on our need, we can go. If it is a normal smart sensors, in general, like current, voltage, temperature, we have to go with very basic standard protocols like IEEE 1815.1 or IEEE 1451 with either it may be a wired or wireless technologies based on our need. So in general, we have to if we are fabricating a smart sensor, we should be in the position to have these standards. We should keep mind in having a standard smart sensors in par with all these IEEE or IEC standards. Next slide, please. So these are the pros and cons of a smart sensor. So very simple. It allows faster system operation. It has a very high accuracy, and it is not achievable which cannot be achievable for an analog control system or a central processing. Though the cost of the smart sensor is high, but the cost of maintenance, ease of program, and ease of adding new sensors are taken into account. So that makes the smart sensors to be very easy compared to the other thing. And though we have so many positives, we have some negatives too. It may not be compatible if it is not upgrading. If smart sensors are not upgraded, then it may not be compatible. And if one simple issue has happened, we have to, because it's a system on chip, and the entire chip has to be replaced. So these are the main pros and cons. coming to the applications. Next slide, please. Next slide. Yeah, coming to the application, the smart sensors can be used in variety of applications, starting from an industrial applications like where we can measure pressure, temperature, humidity, etc. Or it can be used for an automotive, or it can be used for a fingerprint recognition. For children, it can be used as a smart toys, can be used as a pattern recognition. Apart from this, you go with telecommunication. Next slide, please. Next slide, please. The telecommunications are smart dust. It can be used for n number of applications in the field of biomedical, and it can be used for process control too. Process control. So these are the various applications in general about smart sensors. So what I discussed is I've just taken a smart sensor. It's a fabrication technology and its pros and cons with some of the applications. Now I'm going to just deal with the next thing called Internet of Things. Can I have next slide, please? So Internet of Things. So as we know that it's a combination of Internet and things. The Internet provides the capability to connect wild things, the edge devices, which can capture the data and transfer it for further analysis. Sorry. Each IoT solution is a combination of these many things. Combination of sensors and actuators. It is a combination of communication channel and data collection over the cloud, and at the end, information delivery applications. So you should have a cloud, you should have an app, and you should have a communication channel, you should have a sensors. As I said, it's nothing but the combination of all electronics, networking, and with internet. With internet. So can I have next slide, please? Yeah. So this slide, as I said, it's nothing but it's a combination of electronics technology, networking technology, and information technology. Electronic technology includes the basic sensing, actuators, filtering, processing, all can denoising, everything comes into the electronic technology. Coming to the next technology called network technology, it means that it can be used for networking from one part to another part. And the third one is nothing but information technology, where we have all the data has to be stored in cloud that can be used for analysis. We might be knowing about the big data analytics and data informatics. All these things can be done with the help of information technology. So in general, an IoT is nothing but Internet of Things, which is a combination of electronics, network, and information technology. Next slide, please. So coming to the architecture, we have like 4 different kinds of architectures. The first is said to be a 3-layer architecture. The second is said to be a middle layer or wire-based architecture. The third one is said to be SOA, and the last one is said to be 5-layer architecture. Whatever be the architecture, in general, it has an application layer, a network layer, and a perception layer. Whatever be the architecture, an IoT is the one which can be used for identification, sensing, communication, computation, services, and semantics. So this is in whatever be the architecture, it identifies, it sends, it communicates, it computes. It is used for services, and it can be used for semantics. Next slide, please. Next slide, please. Identification. So identification, in the sense, identification is required for IoT to name and match services with their demand from the customer. We'll have some object IDs as object ID, which refers to the name and object address that can be used within our communication network. So the identification method can be like we can go with EPC, that is electronic product code, or U code, or we can go with some addressing method like the recent one is the Internet Protocol version 6. We started with 2, 3, 4, and now we are using IPv6. So these are the various identification methods. Next is for sensing. IoT sensing means that the gathering data related to the objects within the network and it can be sent back to the data warehouse, or it can be given to cloud. Either it will be sensors and it can be actuators, or it can be a wearable sensing devices. Coming to the part of communication, we have like technologies like RFID and near field communications or ultra wide bandwidth. All these things can be used for used as a communication techniques. Next slide, please. Next slide, please. The next thing is nothing but the computation, which is nothing but the processing unit. Either you can go with microcontroller or microprocessor, or as I said, SOC, single on chip can be given, or we can use FPGAs, or it can be a software application which can represent the brain or computational ability of an IoT. In general, the cloud kind of platforms can be used for the computational part of IoT. The services, we have 4 different applications. One, which can be an identity related services, or information aggression, or the collaborative aware services, or use services. So these are the various services which can be done with the help of IoT. At the end, semantics refers to the ability to extract knowledge smartly by different machines to provide the required services to the customers. So these are the various combinations of IoT. As I said, number 1, identification, sensing, communication, computation, services, and semantics. All the combination of these things is said to be IoT. Next slide, please. I'm going to have a case study of a smart health monitoring system. Can I have the next slide? Smart health monitoring system, which is nothing but, I think, the first M health platform architecture. I think it is very clear that the internet or the cloud computation is connected with so many networks, N1 to N1. Each and every network may have so many devices and actuators. Either it will be a medical sensor, it may be a weight scale, or maybe a blood sugar. So many sensors can be connected, so many actuators can be connected with each and every network. Like that, we can have n number of networks which can be connected to the internet. At the other end, you will have a health portal, and the next end you will have a healthcare team. That is the physicians, the doctors will be there in the healthcare team, and it's all stored in a health portal. So initially, the M health approach is nothing but we'll have it has like we can divide the entire architecture into 3 or 4 different segments based on our need. So based on our need, the first is nothing but the collection of patients' data. You can understand that you have an app which is there in a cell phone, and that has to be connected to the health portal through internet. So we can collect all the sensors data. So this is the first segment. All the data can be collected and it can be given to the health portal using an app. The second thing is nothing but from the health portal we'll have a clinician feedback to the patients. So you have a healthcare team, either it may be a doctor or with the help of nurse and other knowledge which he has. He will based on the need of patient, he will through the same app we are giving it to the giving some information to the patient side based on the symptoms and the reports. The doctor analyzes and gives feedback to the patients. The other end, systems feedback to the patient. So it is given to the net health portal, and from the health portal it is given to the patient through an app. So these are the various segments we can divide, and all these segments can be combined. And apart from this, we can also have other thing called data analytics can also be done. Apart from that, the predictive, based on so many information, the predictive technology, machine learning and artificial intelligence can be given, and the predictive technology can be used. But as far as we did, so this is a small case study which I did like 2-3 years before I got a research fund from Department of Science and Technology. and I did this. Can I go for the next slide? Can you go for the next slide, please? So this is in general an IoT in a healthcare. This can be divided based on the services or based on the applications. Services, it can be like various services, that is the Internet of ML or the drug reaction, that kind of services, or the community healthcare, children's health information, or wearable devices access, or semantic medical access, or where there are various services which can be given with the help of IoT in healthcare. Apart from that, we have applications, either it can be a single condition or it may be a clustered condition. Single condition in the sense it can be used only for a single applications like glucose or ECG level, body temperature, pressure, SnO2. All this as a single conditions can be taken and it can be used as an application, or all these things can be combined and you can call it as a rehabilitation system, or it can be combined as a medical management or wheelchair management or imminent healthcare management or smartphone healthcare solutions. So these are the clustered condition, or it can be used for various applications. It can be a single condition or it can be clustered applications. This is this is the way IoT can be used in health care. Coming to the next slide, please. Coming to my DST funding thing, what I did is an IoT based continuous glucose monitoring. It is not just glucose alone. What I took is I took glucose, I took temperature, I took EMG, ECG, all these with various sensors. I have taken all the information and through Android gateway, I have given to the cloud. So cloud, after cloud with some identity based on the identity with RFID. I think, yeah, next slide. Next slide, please. So this is what the IoT based diabetes management, which I did. I have taken like 3 or 4 different, I have segmented into 4 different fields. One, the diabetic management system. The second one, the physician access web. The third one, the nurse access. And the last one is nothing but the monad system, the gateway. With the help of various sensors like glucometer, with what I used is a non-invasive technique, and with RFID tags and cards, which is given to the patient. All these things are stored, and based on these informations, the sensors output and everything has been given to the physician using cloud computing technique. So based on the symptoms and the data of various sensors, physician and application, RFID application, the physician can understand or diagnosis the disease of a concerned patient, and based on based on his experience, he gives these are the things has to be done to as a patient. So with the help of nurse access, if it is a crucial stage, with the help of nurse, he can continuously monitor the diabetes. So this is what the system I did, which has in the cloud computing with segmented with various different systems.